Thank you. So my topic for today is an old favorite. So the temporally lead, and I'm going to add in the name Jones here because I'm going to talk about it as a category at the end of my talk today. So I'm first going to start by just telling you about the temporally lead algebra, probably familiar to a lot of people here, possibly from different directions. All right, so my plan is to give the definition and talk just a tiny bit about the various places that this pops up, to tell you a little bit more about its structure, and then to briefly talk about its categorification. No, not its categorification, that's the wrong word. The category with the same structure. Okay. And so before I start talking about temporally lead, let's introduce some notation so we're all on the same page. So quantum integers have more than one definition, but the one I'm going with today is that quantum n is the ratio q to the n minus q to the negative n over q minus q inverse. Okay, and if you actually do the polynomial division this represents, you get a bunch of q monomials, and they're symmetric in their powers. And how many of these are there total? How many total terms are there in here? There are n total terms. Okay, and so as you might expect, if we specialize to q equals 1, well, we're in a little trouble if we think of this as our definition, but according to this definition, when q equals 1, quantum n is just n. Okay, so good stuff. And in general, quantum 2 is q plus q inverse. I maybe didn't need to say that, it's pretty obvious from here, but quantum 2 is special. It's going to be a recurring character throughout this lecture. So here's an exercise. Quantum 2 times quantum n gives me quantum n plus 1 plus quantum n minus 1. Okay, if we specialize to q equals 1, we see that it is in fact a true statement.
You've written plus twice.
Yes, I have. Thank you. I was wondering why people were looking at me funny. Okay, good. Much better that way. So now it is true as a statement about integers n, and also true as a statement about quantum integers. And we need these quantum integers to define the temporally lead algebra, but let's start with temporally lead diagrams. Okay, so it's pretty straightforward to draw a temporally lead diagram. You pick some integer n, well, not negative integer n, and you draw n points along a strip at the top and another n points along a strip at the bottom.
Sorry, just back to the quantum. What is your convention for quantum 0? Is that 0 or 1? Just depending on how you'd expand.
You know,
Or probably 0. I guess.
Have not asked myself that question, but let's figure it out, right? Because quantum 2 times quantum 1 should be 0 plus 2, and quantum 1 is actually just 1. Okay, so n points on the top, n points on the bottom, and we want to connect these points up while staying within this strip and without crossing any of the lines we create. So if I just put my pencil down and start marking, I can get myself into trouble, so let's be a little bit careful. So this is an example of a TL6 diagram. Okay, that's it. That's a temporally lead diagram. Here we can write down that the important things were that we had these non-crossing strings between all points, and the strings must stay inside the given strip. So when I write n, and I'm going to need a parameter q in a minute, I mean algebra for now over the field of C adjoin Q. Okay, and so what do we need to have an algebra? We need a vector space and we need a multiplication. Turns out we're going to have a lot more than that, but those are our starting pieces. So we want to have a basis of these TLN diagrams. Okay, so for any fixed value of n, we throw in these diagrams and we say that they're linearly independent.
I'm sorry, what do you mean by over C of Q? What does that mean?
So for now, Q is just an unknown variable, so I'm adjoining.
Oh, I see. Okay.
Yeah, we have not specialized Q yet.
Got it. Thank you.
Okay, we have a basis of TL diagrams, meaning that addition in this context is formal, right? I can write down, say, a TL4 diagram plus some coefficient from my field times some polynomial in Q and Q inverse times another diagram. And that's just, it is what it is. There's no simplification at work here. But we have more interesting multiplication. Multiplication is by stacking our diagrams one on top of the other. So if I write A times B, I want to look at the diagram I get if I put A on top of B. So the top n points of A and the bottom n points of B get matched together. Okay, and let's do a couple examples of this. How about in TL4, we'll take a frowny face and multiply it by this diagonal thing. And what do we get? So this one goes on top. And this goes on the bottom. And now, would have been good to say back here that we only consider these diagrams up to planar isotopy. Okay, meaning that if you can shake the strings around a little bit in the same strip of the plane, then you have the same diagram. Okay, right. And so this is just a funny way of drawing this element of TL4. Okay, and our multiplication here is extremely non-commutative. What if we took these same elements and took their product in the other order? Well, then we would have this one on top, and we'd get this on the bottom, and we now have this diagram, but we have this additional data of a free floating loop. Okay, and these TLN diagrams are essentially combinatorial, right? We're interested in the data of which points match up with which other points. We're not interested in the specific topology or geometry, I guess, of how we draw the lines. And so there's not really room in that description for an extra circle. So what we do is we throw it away. But if you object to that, if you want to remember that it was there, then we say that every one of these free floating loops gives us a multiplicative factor of quantum 2. Okay, and so of course, in a diagram that had a lot of loops, we just pick up one factor of quantum 2 for each loop there, and it doesn't matter how it sits in the diagram. So this is 4 powers of quantum 2 times the diagram with the loops removed. So what is the multiplicative identity here? Straight lines, yes, indeed, right? If we have any picture and we add these either at the bottom or the top of the picture, then we just have the picture we started with. This is the identity in the fourth temporally Lieb algebra. Okay, now there's a lot more structure. And probably the least surprising one of these is that there's a tensor product given by horizontal concatenation. Okay, so if we have a temporally Lieb diagram tensored with another temporally Lieb diagram, then what we get is just the result of setting them down next to each other in the plane. Right, so tensor takes a TLN diagram and a TLM diagram and gives you back something on n plus m points. So we also get a trace defined diagrammatically. Okay, so if we have a temporally Lieb diagram X and we connect every string on the top with the corresponding string on the bottom, then what we get is some number of loops, right, between 1 and n of them. Okay, and so that's the trace on our basis, and we just take the linear extension of that. Now, one thing we expect traces to have is the property that you can cyclically permute the inputs and you still get the same answer. So we'd like trace AB to be the same as the trace of BA. And well, if you think about it, first we multiply A and B, we match up the bottom points of A with the top points of B, and then we match up the top points of A with the bottom points of B. And so we've just really glued these together along both boundaries, right? And so this is the same thing as doing it in the other order. We also have among the different temporally Liebs. So if we're in one temporally Lieb and we want to think about what's happening at the next level up, we can just take our picture and add a string on the right-hand side by convention. Okay, and so this is why we don't really think of temporally Lieb as a bunch of different algebras, but a single family of algebras. Once you've fixed your value of Q, as long as you're dealing with Q either as a variable or you have the same value of Q between these, then you get this family of maps. And these are almost invertible. Okay, meaning that we have maps in the other direction. If we wanted to go from TLN plus 1 down to TLN, we could take our box B and we could just think about it as a box with one fewer strand on the top and the bottom by connecting the rightmost strands, right? And if we first included an element up into the next level and then applied this operator, we would just create a free floating loop on the outside. And so we'd get back what we started with, just with an extra value of quantum 2 thrown in. Okay, and so this gets called the partial trace, because if we did it enough times, we would get the actual trace back, or the conditional expectation. Okay. One more thing. Finally, we also have an involution corresponding to horizontal reflection. Okay, so let's pick a letter with sufficient symmetry, say R. Okay, so the involution of a box R is just the reflection of that box. Okay, and it's good to have this in the algebra because, of course, we do have this essential symmetry in these diagrams that the sort of choice of which points go on the top and which points go on the bottom are arbitrary. Absolutely, yeah. They are different, yes. And in particular, there's like a lot of versions of a lot of these things, right? This is not the only way to include TLN into TLN plus one, put the strand on the right, or you could put the strand on the left. Right, so we just make a choice so that we have something concrete to be getting on with.
And do we also have that tensor is commutative under trace?
Yeah, that the trace of A tensor B is the same as the trace of B tensor A, because when you do the trace to these, the A and the B don't interact at all, right? And so each of them is just some collection of circles. Doesn't really matter which one gets drawn inside the other one.
You specifically have that would be trace, also the trace of A times the trace of B, correct?
True.
I feel like these trace operations are going to be problematic if you choose your quantum 2 to be 0. Do you renormalize, or is there some generalization?
I would never ever choose quantum 2 to be 0, so I do not have the answer to that. I would love to hear from you why quantum 2 equals 0 is interesting.
Semi-simple one.
Yeah, non-semi-simple. So
Yeah, the only interesting one.
let's continue this discussion later. Yeah. Right. So, oh, this one? Yeah, that's a times. Yes, that's a T. Good. More questions. Okay. So we have this family of algebras with really quite a lot of structure on it, right? And so now seems like a good time to talk about why we study this, yeah? And it pops up in a lot of different places.
One more question. For general Q, semi-simple, we know it's the type importance.
I will get to that. Yeah.
Sorry.
No, it's a good question. I like it. Okay, so why are people interested in temporally leap? Well, okay, so Temperley and Leib began studying this in the context of statistical mechanics. I don't recall exactly what they were trying to study, but that is, as far as I know, the first occurrence of this algebra. And I believe the next place it showed up is that Jones discovered it in subfactors. So Jones discovered a copy of TL in the so-called standard invariant of a subfactor. Seems like a good time to mention that this is really where this was the angle that I began approaching this topic of diagrammatic categories from, that my background is in subfactors. And so, yeah, so there's this standard invariant that I might define later this week if time allows, or at least talk about some. And inside of it is a copy of Temperley Leib. And if you have a subfactor A inside B, okay, so factor, subfactor, then Jones defined an index which measures the relative size of A in B and proved some great theorems about this. And so in particular, the copy of Temperley Leib that we have has its TLQ, where Q is the solution to the Q that makes quantum 2 squared equal to the index of your subfactor. Okay, and Jones's index theorem says that, this index that measures the size of A within B is, of course, a positive number. And you might think that, in analogy with finite groups, it was an integer, but in fact, it does not need to be an integer. It can be any real number, 4 or greater. And below 4, it can only be one of a countable set of numbers of the form for cosine squared pi over n, where n is 3 or greater, for any real number above 4, including infinity. Right, and so this in particular is why the possibility of 2 being 0 or q being 0 is not something I've ever thought about.
So by saying you discovered a copy, do you mean it's an algebra object inside the category? Invariant at category or
So the standard invariant is many things, and it is a category, but when Jones first started talking about it, it was viewed as a infinite family of endomorphism algebras. And so from this point of view, he really discovered the temporally Lieb algebra in family of algebras inside another family of algebras. So by the way, this occurrence of temporally Lieb in the standard invariant of a subfactor is what led Jones to define the Jones polynomial. Okay, so the Jones polynomial in its sort of historic form is a map from the braid group to TLN. Okay, I might get to this in a couple minutes, but there's a presentation of temporally Lieb in terms of generators and relations that makes the fact that there should be a connection with the braid group pretty clear. I can say that with hindsight, right? I mean, it was sort of astonishing when it was first found. But okay, and finally, if you were looking at the representation theory of UQ SL2, you'll end up looking at diagrams like this. Okay, and so we get the, if you think about that categorically, the diagram category is the temporally Lieb Jones category.
I don't know if this question will go too far afield, but since you're talking, I've seen Kaufman's name associated with this thing. Is an easy way to say what he did?
Yeah, the one sentence version is that Kaufman, and I'm glad you brought this up because I should say Kaufman gave the diagrammatic presentation of the temporally Lieb algebra. Okay, it was an algebraic object without diagrammatics before, and Kaufman was the one who observed that we can represent it using these diagrams in this really straightforward way. So that was his contribution, and he also showed how we can think about the Jones polynomial as coming from a map of diagram algebras between tangles and temporally Lieb algebras. So I promised you at least a little bit of the structure of temporally Lieb. And so there are two things to say here. And I guess the zeroth thing I will say is that from now on, I'm going to assume that Q is a real number greater than 1, so that quantum 2 in particular is greater than 2, but specifically non-zero. Okay. A lot of what I'm going to say does not entirely require that, but that is the simplest context. If you're very curious about what happens if you relax those assumptions, do ask me, and I will tell you the things I know, but this is going to be our baseline from now on. Okay, so the first thing I want to say is that TLN is generated, multiplicatively generated, by projections EI, which we will define to be a lot like the braid group generators. So they'll have mostly straight up and down strands. And then in one place in the middle, they'll have a cup and a cap. And then nothing but straight up and down strands from there on out. Okay. Let's see, this is at the ith position. And I'd really like for this to be a projection. And so I'm going to put a factor of 1 over quantum 2 in front of it. Okay, so check for yourself that this is a projection. What about the fact that these multiplicatively generate TLN? Maybe I should say I goes from 1 to n minus 1. Let's do an example. Okay, what if we had I'll do something easy, but the idea is not really any more difficult. What if we wanted to represent this as a product of EIs? Well, basically, you can see that at the bottom level, you have a cap. And so if we put a cup above it, then we could connect this string up to there and move it further right in the diagram by having it go through that. And now we've created another cap. And so we need a cup above that. And we can now connect this leftmost string to that to get it where we want to be. And we have one final cup there. Okay, so that's the idea in a very simple case of why these generate your whole temporally leave algebra. That these satisfy are, I mentioned that they were projections. So each of these is fixed by the involution and is equal to its own square. And one more relation that we need, well, a couple more. If I and j are far away from each other, then EI and EJ commute. Read up your diagram, it doesn't matter which cup cap location you put in first, as long as the strings that they're on don't interact. As long as this is greater than 1, they commute. And let's get this one right. If I have EI times EI plus or minus 1 times EI again, I get my original EI back. Okay, and the diagram for this, if you want to check this diagrammatically, it just looks like this. And this was the relation that Jones looked at and said that looks like the braid group relation. It's not the braid group relation on the nose, but it's the same sort of relation you see in Reidemeister 3 or in like the Yang-Baxter equation, right? And so he played around with taking a homomorphism from the braid group generators to temporally leave until he found the right thing to send them to create an invariant of braids.
In the last relation there, you showed us a diagram worked out, but you also have these factors of 1 over 2q.
Oh, I'm probably wrong up to a factor.
Yeah, there should be some,
Yeah, thank you.
maybe square.
Does that look better? No, there's 3 of them on this side, and maybe it should be in the denominator.
There's no bubble.
But there's no closed loops in the picture that you have on the right.
Purely because of the fact
There's a factor out front.
Oh, yes.
Yeah, yeah.
There's 3 of those.
if you don't have that factor, the original relations correct.
That's right. But if we don't have this factor, then it's not projection on the nose anymore. So
It seems to me, shouldn't the on the right hand side of the diagram that be straight lines through, not a cup and a cap there?
where?
On the bottom diagram, on the right side, there's this cup and a cap, and I don't know why.
That's a straight line.
Yeah, but to the right of that, to the left of that. Because it seems like all the cups and the caps are on the left-hand side, but then there's this other cup and cap that's just there. I don't know, you have a cup. You have like, right, you have a cup and a cap at the top and the bottom of that. Yeah, those.
Okay.
I'm just kind of trying to figure out where those are coming from.
Oh, right. So here is
Yeah.
E1,
Oh, there's
E2, E1.
There's an equality there. I thought this was one diagram.
No, sorry. There's an equality here.
Okay, that makes more sense. Yes, I was very confused.
Okay. Okay. The second thing that I want to tell you about the structure of temporally leave is that in this case where quantum 2 is greater than or equal to 2, we have a semi-simple algebra. Okay, and so of course, in this case, if we know that something is semi-simple, we might ask ourselves, well, then what are the simple ingredients here? Okay, so what are the simple summons of TLN? Okay, and I'm going to give you only like an outline of how to think about this, but to answer this question, we want to understand projection in TLN, right? So a projection has the property that it's idempotent and it is its own star, up to isomorphism. Okay, and so now I need to tell you about isomorphism and temporally Lieb. Okay, so and this is the operator algebra's definition of isomorphism, that two projections P and Q are isomorphic if there exists X in TL, now this is a new thing, TL n to m. Okay, so instead of having endpoints on the top and endpoints on the bottom, I'm going to have a different number of points on the bottom and the top. Okay, so this is TL style diagrams from endpoints on the bottom up to m points. Okay, it's no longer an algebra, but it's still true that you can compose diagrams if you have the range of one matching up with the domain of the other, and all the usual things we've established for temporally Lieb, like closed loops, tensor product, etc., are the same here. Okay, so I had to interrupt myself in the middle of describing isomorphism to say that. Right, so P is isomorphic to Q. Let's say that P was in TLN and Q was in TLM. And they're isomorphic if there exists an X that goes from N to M, such that I'm going to draw X in a trapezoid so that here's X, starts with N points, goes through M in the middle, and then I'm going to put X star up above so that this is equal to the projection P. And if we arrange X and X star in the other order, we get the projection Q back. Okay, so if there exists an X that does this, that when you combine it with its star in one way, you get P, and if you combine it in the other way, you get Q back, then we have an isomorphism of projections. Okay, and I'm going to probably come back to this later in this week because it's a useful idea. But for now, I'll just give away the punchline, which is that we can classify the projections of temporally Lieb up to isomorphism. And there is one for each n. So for every n, there's one new projection in level n that you haven't seen its isomorphism class before. These get called the Jones-Wenzel projections, okay, denoted by F with n in parentheses, which is in TLN. And it's the unique element with the following properties. Okay, so it should not be 0. And it should be, in fact, a projection. And so far, that's not very interesting. So the one remaining property that we add, the one that completely characterizes it, is that Fn is uncappable. Meaning, if I had this basis element, sorry, not basis element, Fn in particular is not a simple temporally Lieb diagram. It's a linear combination of all, actually, of the temporally Lieb diagrams. But if we take this element and we put a cap anywhere along the top, and since it's its own star, equivalently anywhere along the bottom, we would get back 0, right? So same thing if we put the cap anywhere along the bottom. Okay, and now you might like to complain that with this operation, I've moved out of the temporally Lieb algebra. It's true. So, but this statement still holds inside TL n to n minus 2 or n minus 2 to n.
If you didn't want to leave the temporally Lieb algebra, could you just equivalently say that if it was 0 when composed with any of the generators?
Exactly.
Okay.
Yeah, that's right. Okay. I don't think time is going to allow me to even outline this, but let me just state the theorem is that Fn exists and is unique in TLN. Yeah, I have this as a series of exercises, but I'm going to skip those. If you're interested in them, talk to me afterwards, and I'd be very happy to tell you how that goes, because I did promise that we were going to connect up with categories. So I should do that. Oh, yeah, but I should have said that this gives us a complete classification of the projections in TLN, and therefore the simple summons. Okay, so the representation theory for Q more than one is completely deducible based on these creatures. Now, okay, I'm going to start by giving a non-standard definition. And the reason is this. Okay, so first of all, let me give the disclaimer that, like I said earlier, I came to tensor categories through subfactors, through operator algebras. And so it's one of these situations where my instincts keep telling me that there is only one really interesting kind of tensor category, and that everything else is just adjective salad. But I understand that if you came at this from any other point of view, you think the same thing, but you think that what I'm about to say is just some sort of adjective salad. So, okay. I mean, there's a lot of adjectives, right? And not everybody uses the same adjectives. So it's a problem. All right, so the thing I'm going to define has much in common with what gets called a tensor category, but is just different enough that I'm going to put a silent P in front of tensor. Okay, so a tensor category, the P stands for, take your pick, planar, or maybe pivotal. Okay, but this kind of tensor category does not stand for Peters. It would have to be a capital P. So it's C-linear. Okay, all of our Hom spaces are vector spaces. It is a rigid monoidal category, which means I will remind you of the definition of this in a little bit more detail with diagrams in a minute, but remember that this means that we have a tensor product and a notion of dual. It is Karoubi complete. Okay, so this means that we want it to be additively closed and idempotent closed. This gets us much of the way to abelian without actually needing abelianness. We also require that all of our Hom spaces, which we know are vector spaces, are in fact finite dimensional. Finally, we require a pivotal structure. Okay, and I'm going to take a minute to unpack rigid and pivotal and what they mean in diagram categories, since that's the excuse for my series of talks.
The only thing that is losing is the kernels, right?
Sorry?
The only thing you're losing is the kernels are comparedness.
What I'm missing from like being an abelian category.
Yeah, but that's the only thing basically.
Yeah, that's right. So to say it's idempotent complete is to say that we have kernels and co-kernels for the projections, but not for everything. In a rigid monoidal category, remember that we have, let's for now say our element is L. So an object L is left dual to an object R, or equivalently, R is right dual to L if we have eta, a map from the unit into R tensor L, and also a map epsilon from L tensor R into the unit such that we get the identity on L by composing, what do we want here? We want epsilon composed with, okay, and a similar equation for the identity on R. And I'm skipping writing these down and talking about them in detail because in 60 seconds, I'm going to give you pictures for them. Okay. So as diagrams, we're going to add to the sort of pictures we were drawing yesterday an orientation on our strands. Okay, so we have a strand with an up arrow. Our convention is that'll be labeled by L. A strand with a down arrow will be labeled by R. And eta goes from the unit, the empty diagram, to R tensor L. So here's R, here's L, and R is labeled with a down, and L is labeled with an up. And epsilon is going to be a cap, and it goes from L to R. So this one is labeled oriented like so. Okay, and so the structure of having two objects that are dual to each other is being able to connect them up in these two ways. Okay, and now the relation that I sort of glossed over here is a string straightening relation. The identity on L is equal to, and now we can do a type check. This is, I drew the wrong one. Here we go. Try this again. Okay, yes, this is the epsilon cap that we have right here. And this one is oriented the same way that eta is oriented. And so this is the diagrammatic statement of this claim. Okay. And similarly, if I drew the strand with a downward label so that now it was the identity on R, I would have the other one of these. And you could check that the ingredients in here are the cap and the cup that we have access to. Okay, so the thing about this that's very frustrating is that you only, if you just sort of started drawing, as you saw here, 50% of the time, you'll draw a cap or a cup that's not in the set of caps and cups that we are working with. So we are particularly interested in pivotal categories because they solve that problem. They give us all of the caps and the cups that we need. Okay, so a pivotal category is a monoidal category with duals, okay, meaning that every object there has a right and a left dual. It's pivotal if it has an isomorphism, really a tensor isomorphism, pi x between x and its double dual. Okay, so that's new notation, but the star is the dual. So two of them is a double dual. The monoidal category of duals is pivotal if it has these isomorphisms for all objects x in the category. Okay, and what this means is that the dual structure already gives us that we have x and its dual oriented like so. We get a cap. If we have x dual and x, and the orientation now must be like this, we get a cap. And now we can create the missing cap and the missing cup by, now let's see, what we'd like to do is have x and x dual in the other order. And that means that we go like this. And we create this using our pivotal structure, right? So here's x dual, and here is x double dual, right? And of course, since we have this for all values of x, we have this for x dual and x double dual. And then we put our pi x in here that sends x to x double dual. And we get this. So whenever we draw this kind of cap, we mean use the pivotal structure to create it. Okay, and similarly, which cap are we missing? We're missing this. And so create this by orientation, by putting pi inverse in this spot, going from here, x double dual back to x.
On the right-hand side of the equality, wouldn't the arrow be going in the other direction because you're using the old cap, right, which has the arrow going from left to right? So in the arc coming out of the pi, so the upper arc, you've got the arrow going left. But it's supposed to be the cap. I guess it just depends on your conventions, but
I'm not sure what the question is.
Saying that because x double dual is the dual of x dual, should your arrow be going the other way?
Should,
So you can use the cap on the top left.
I see. Well, so, okay, so now we get into the actual problem here, which is that really when we have, really what I should be doing is I shouldn't be writing the duals at all, that I should be writing x, and we should have the convention that when the arrow goes up, it is x, and when the arrow goes down, it is x dual. But of course, that doesn't even make sense until you've got the pivotal structure. So let's just gloss over that for now. Yeah?
Definition of pivotal, that isomorphism has to be denoted.
Yes. Yes, it should respect our tensor structure.
Should be I guess maybe explicit should be natural isomorphism. Natural maps.
Okay, yes. Okay, I am running low on time. And so we'll come back to pivotal categories tomorrow, okay? But I want to end with telling you about temporally lead category as promised, right? The temporally lead Jones category, TLJ. Sure, we need to include a Q in here, in fact, is the Karoubi completion of the linear monoidal category given by, okay, our objects are just non-negative integers thought of as points on a line, okay? And our morphisms from, say, n to m are just these TL NM diagrams, okay? Modulo the usual relation, which is that a closed circle counts for a factor of quantum 2. I've tried to make it clear that this is not 0, but it is a circle by drawing it slightly larger than everything else. But let me just say that out loud also, so it doesn't get lost. Okay. And, you know, as we've already seen, the composition in this category is what we get from stacking morphisms, and tensor product is, bless you, horizontal concatenation. Okay, so, you know, before I threw the words Karoubi completion here, this was actually a pretty simple category, right? You have one object, every integer 0 and higher, and you have your temporally lead diagrams as your morphisms. Okay, and in fact, we don't make things too much worse by throwing in this phrase Karoubi completion, because basically what we need is to have that it's idempotent closed. And so we need to add objects corresponding to, in particular, the co-kernels of, have I erased these or are they still here? Oh, look, they're still here. So for my projections in temporally lead, I need to add in their co-kernels. Okay, and so that's what we gain when we do the Karoubi completion, slightly more objects, same structure here. And in particular, there's a universal property at work, so that anytime that you have a tensor category with a silent p, where you have a single object with pivotal dimension quantum 2, and which is symmetrically self-dual, then you get a pivotal tensor functor from TLJ into that pivotal category. And so this is a little bit like in a Lie algebra when you have a bunch of copies of SL2 sort of picking out your sort of most fundamental unit. What we have here is Temperley-Lieb, the representation theory of SL2, picking out our simplest objects for some non-technical meaning of simplest. That's where I'm going to stop.
Okay, so there's already been quite a few questions. So in the interest of people not being separated from their lunch, maybe just short questions. No questions is very short.
Yes.
Yep.
If Q is not generic, it's not greater than 2. If you take Q non-generic, this you can still do this Caro completion.
I think so. If it is not generic, if you have a value of Q that's less than 2, then the representation theory changes with the particularly some of these Jones-Wenzel projections might have 0 trace, or and so you might not be working with in a positive definite setting anymore, but I don't think the Karoubi completion requires that.
If there are no further questions, then let's thank Emily again.